Well, hello, I'm Tim Fuller-Rowell at the University of Colorado and based at the Space Weather Prediction Center at NOAA, the NOAA Space Weather Prediction Center in Boulder. And I'm going to talk, or first of all, thank the organizers for the invitation to present this talk. I'll be talking about the current status of finite difference models of the couple, mainly the upper atmosphere, but most of those upper atmospheric models now have some connection to the lower atmosphere. So they're more atmosphere-ionosphere models rather than just thermosphere-ionosphere models. And I'll also talk a little bit about some of the possibilities for the future. There's quite a large team of people that have been involved in the development of the model I'll be talking about, which is the whole atmosphere model, WAM, and IPE, the ionosphere plasmasphere electrodynamics model. But a lot of people in Boulder, and we also work with the team at the Environmental Modeling Center on the east coast of the US, Mark Iredell, Henry Wang, and Morphy Shravanis. And I'll be talking about this whole atmosphere model, WAM, the ionosphere plasma electrodynamic model, which is the plasma component. And also we have a data assimilation system that enables us to follow real weather conditions. Now this WAM IPE model, it actually is a development of a CTIP model over the years. CTIP was the coupled thermosphere-ionosphere plasmasphere electrodynamics model. The thermosphere was developed in about 1981, coupled to a high latitude ionosphere from Sheffield University in '84, and then a plasmasphere component also from Sheffield in 1990, and the NCAR electrodynamics component was coupled in at the same time. So that basic CTIP model has been used for many studies over the years and has been running at CCMC in the US and operationally actually at NOAA. And in about 2006, we extended the US weather model to 600 kilometers so that the neutral component of CTIP was now a whole atmosphere model called WAM. And a little bit later, in about just about 5 or 6 years ago, we also improved the global ionosphere and made it a global seamless distribution of flux tubes rather than combining two separate components, but it was also coupled in with the electrodynamics component. So we now have a WAM IPE model, which is coupled through using the Earth System Modeling Framework, which is a 3D regridding system. So I'll be talking mainly about this WAM IPE model. In terms operationally, obviously we want to get the physics models to a state where they're useful operationally. And currently at NOAA, there's 2 operational models. We have the WSA-NLIL, which follows the propagation from the sun to the magnetosphere. And then the Michigan geospace model captures the response of the magnetosphere to that plasma coming from the sun to produce geomagnetic activity predictions. And the National Weather Service is also committed to raising the lid on the US weather model to improve the long-range seasonal and sub-seasonal terrestrial weather model. So it's presented an opportunity to maybe extend this sun-to-earth modeling system to include an operational thermosphere-ionosphere physical model, specifying and forecasting the space weather in the upper atmosphere for satellite drag and anything that's impacted by radio communication. And so and the whole atmosphere model provides which is part of that operational system, provides the impact on the upper atmosphere and ionosphere, the forcing from the lower atmosphere. And of course, it has to include the forcing from solar and geomagnetic activity. So we're looking at all the main forcing components of the system and hopefully bringing the understanding of the physical system together in these models. In the impacts of the upper atmosphere on operational systems, of course, the obvious one is satellite drag for objects in low Earth orbit. You need to know what the neutral density is for orbit prediction for space traffic management. just to avoid collisions. And you can also follow the re-entry and try to predict where they're actually going to re-enter the atmosphere. And it's mainly the neutral mass density, of course, which is the impact on satellite drag. Winds partially, and we're not quite sure exactly how much the actual structure and waves through the system is a big impact. Obviously, it depends on the scale and size of that structure. And of course, for the impacts of the ionospheres on the radio wave propagation, there's two sort of main systems, but there are more, of course. But the HF communications, the 3 to 30 megahertz, and of course the D region absorbs those signals, and any structural gradients or undulations in the ionosphere until can scatter the signals so that they don't the propagation is not where you expect. So for HF communication, of course, you need the ionospheric layers, particularly the F region, in order to reflect those signals so that you can communicate from two ground sites or from, say, an aircraft and ground stations. And the other category is more the satellite communication, which includes the navigation, timing, positioning. And in that case, the line of sight radio wave is passing through you want it to pass through the ionospheric layer. And in this case, the ionosphere is a nuisance. And the total electron content along the path of the radio wave causes a delay and can refract the signals, causing them to bend. And the plasma irregularities in any structure and gradients can diffract the signals, which can cause amplitude and phase scintillations and sometimes complete loss of the signal completely. And there's the and the communications, of course, is another aspect of that, as opposed to the satellite navigation. So they're the sort of the main reasons why we want an operational thermosphere ionosphere system for those main applications. So the whole atmosphere model that we've developed is, as I said, it's an extension of the US weather model. We started with the previous version of the NOAA weather model, the global forecast system with the spectral dynamical core. We extended that, which was went up to 60 kilometers, then up to 600 kilometers, 150 layers, variable G because of the altitude extent. And that's run at a spectral resolution of T62, the spectral truncation, which just tells you the number of wavelengths it's resolving, which is equivalent to a resolution, a grid point resolution of about 180 kilometers. The operational model runs at more like 10 or 12 kilometer resolution, but we can't quite afford that yet. Something for the future or something closer to that. And of course, it includes all the lower atmospheric processes, all the tropospheric weather and stratospheric dynamical process. And of course, we had to add all the additional thermosphere and ionosphere physics into that system. And so the WAM part, it provides the 3D neutral winds, temperature, neutral density, the major species composition. And the WAM, of course, is coupled to the, as I said, to the IPE model, the ionospheric component, using the assisted modeling framework, 3D regridding capability. The benefits of WAM, because it's compatible with the current operational model at NOAA, you can actually implement the data assimilation system, the GSI, the grid point statistical interpolation, which is the sort of the older version. Now moving on to different systems called JEDI, but since the WAM was sort of based on that operational GFS model, even though it's extended, we were able to use that same grid point statistical interpolation in the lower part of WAM, so you're able to follow real lower atmospheric weather events, you know, the strength of tropical convection, things like that. And follow their impacts on the upper atmosphere and ionosphere. And of course, we can also benefit from all the improvements in the lower atmospheric physics and all the expertise at the Environmental Modeling Center, which is the main developer of the operational NOAA weather model. And so we benefit from all those improvements, and one particular one is the for the National Weather Service has already replaced the spectral dynamical core with the non-hydrostatic FB3 from GFDL, and which includes the non-hydrostatic processes. And so we will be able to incorporate that new dynamical core at some point. So just examples of some of the sources from the lower atmosphere that the WAM model running in operations would be able, with the GSI data assimilation, would be able to follow. One is the strength of the tropical convection, here sort of depicted as the number of lightning strikes over, I think it's over a year. But, it shows the longitude dependence of the tropical convection. And so that imprints a longitude structure of waves that propagate up into the upper atmosphere, and the longitude structure in the winds in the dynamo region of between 100 and 150 kilometers actually creates longitude structure in the ionosphere. You create a longitude structure in the electrodynamics, then those electric fields can be felt all through the layers of the ionosphere and can move the ionosphere around. So you see that ionospheric longitude structure imprinted on the air glow from the O+ recombination at about 250 kilometers altitude. And then if you have changes in the stratospheric circulation, things like sudden stratospheric warmings, they can modulate the tides that propagate up into that same dynamo region and can, again, drive the electrodynamics. And that can actually change the plasma content by 50% for a particularly large event that occurred in 2009, the sudden stratospheric warming of 2009. And the spectrum of tides can also propagate up and produce a feature that has never been modeled before, the midnight temperature maximum. And now, because we have things like the turdinal tide particularly, that tends to propagate up very effectively up into the upper layers. And you can see the impacts on around midnight, plus or minus a couple of hours. You see it in a temperature and wind and neutral density signal, which again impacts the ionosphere. And in fact, you have a whole spectrum of waves in the lower atmosphere that is causing variability in structure in the wind's temperature and composition, which we think is also can possibly trigger ionospheric irregularities. You can see these waves propagating up from the lower atmosphere, and what it looks like in the vertical winds over on the left, bottom left. You can see the structure of all the undulations and wrinkles in the atmosphere. So looking at some of those applications, how well can we actually predict the neutral density? This is just an example of running the model and then sampling the model at the altitude of the Gochi satellite, which is at around 250 kilometers altitude. This was a period of a fairly modest storm in March 2013, so-called St. Patrick's Day storm. And you can see that this is just showing 3 days, and each of these orbits, you can see the double peak, 2 peaks and 2 troughs along the orbit. And that's a polar orbiting satellite just passing through that structure you see over on the left-hand side. And the first thing, the obvious thing, is that it doesn't look a bit like what you expect from just a thermosphere-ionosphere model or an EMSIS model. It's a very structured, it's not all uniform like EMSIS, like an empirical model would be. You can see all the structure, and you can actually see that midnight temperature maximum there. And so the satellite is passing from pole to pole through this global distribution. And this is a comparison of the neutral density inferred from the accelerometer observations on that Gochi satellite compared with the WAM model. And you can see that along each orbit, you're actually capturing the global diurnal and latitude structure really well. This is just the quiet day, and you can see it's actually following it to within about 10%. And during the storm, it's a very modest storm, so there's only about a 30% enhancement in the background neutral density. But you can see, obviously it departs a little bit, it's not perfect, but you can see it still captures a lot of the global structure. And then as you follow into the recovery, on this March 16th, you can see it's starting to look like a quiet day again. So it's sort of reasonably encouraging just for a fairly modest storm. In this case, we actually didn't do any tuning. That was sort of out of the box, which is, that was just sort of surprising. And you don't actually need that. Normally, you have to sort of normalize a little bit the quiet day to do that, because there can always be some things that cause DC offsets in the background levels from mixing of the lower atmosphere or semi-annual variations and things like that. We try to capture as many of those as we can, but of course there's always going to be some residual. But you can see even with this, the accuracy of the model, even through the storm, is within about, I think it was about 15%, 10-15%. As we get to larger storms, if you step up, this was the magnitude of the DST for the one that I just showed in 2013. And on St. Patrick's Day, 2 years later, there was actually a much bigger, well, not a lot bigger, but a significantly bigger storm, a much stronger storm, the DST of 234. And then if you go back to November 2003, that was actually a very major storm with a DST of minus 472. So how does the model do as you step up in magnitude? This top one was the one that I just first showed. And we always don't have the Gochi for all of these storms. Here we have the grace at slightly higher altitudes. Higher altitude you go, the storm increases tend to be larger. So this is probably more equivalent to the Gochi increase of about 200%. But you can see, again, it's capturing both the global structure and the storm response. The lines sort of through a lot of the bumps and wiggles are the orbit average values. And then if you go to the November 2003 storm, the very, very major storm, again, you can see it follows it reasonably well. This is again at Champ altitude at 400 kilometers. And this would be equivalent of about a 50% at that altitude, let's say a 50% increase at the Gochi altitudes compared with Champ. So you can see that's a factor of 10 increase in the magnitude of the storms. So you can capture the whole range, and of course the scale is different because this response is 10 times this response in neutral density. But again, it's capturing, and so there was no tuning of the model after we obviously tuned the basic model, validating the model. Then this is the results that you get. Of course, if you have the right amount of energy input, you have the right amount of global circulation, we hope. And then it's the global circulation then that is moving the major species composition around. And you calculate this type of global structure of neutral composition. And this O to N2 ratio is important because it controls the loss processes of the ionosphere. It also controls a little of the thermal expansion because of the scale height differences and the density that you would experience at a given altitude. But a lot of the O to N2 ratios, the impact is on the ionosphere. And if you're in a region where you have strong upwelling, where these blue regions are, where the O to N2 ratio has decreased, so you have a lot more N2, it can cause a negative phase in the ionospheric storm. This is just an indication of the sort of the temperature change that you can get, and you can easily get temperatures up to 2000 Kelvin during a significant storm. And of course, we have the ionospheric component, the ionosphere plasmasphere electrodynamic component, that we use the output from the WAM. You feed that into the ionospheric component to produce these space weather products in operations. And this model is actually based on Phil Richards' FLIP model, which is much more sophisticated photochemistry, solves for all the usual species. Most of them are the ones that are transported are the O+, H+, and N2+. And you just create a global network or seamless network of flux tubes at about a couple of 100 kilometer resolution in latitude and 400 in longitude. And you have perpendicular transport using a semi-Lagrangian system. and a resolution that roughly matches the WAM model of roughly 200 kilometers horizontal resolution. And it's in the, you can see the distortion here of the flux tubes and the background plasma density, because it uses the IGRF, the International Geomagnetic Reference Atmosphere, the apex coordinate system. So you have realistic structure from the geomagnetic field effects. And of course the self-consistent dynamo from NCAR's Art Richmond and Astrid Mort. And of course the coupling, as I said before, through the system modeling framework, and it's all using MPI, parallel processing. So validation of that, it's some good validation against the Cosmic 1 satellite building. So this is a monthly average picture of the observations from Cosmic in December compared with a standard sort of quiet simulation. You see that the structure is very reasonable. And this is just looking at some of the impacts of the waves that you get from observations on the top right at the incoherent scalar radar at Arecibo from the paper by Juth. And you get similar structure from the variability of the waves that's coming up from the lower atmosphere. And of course, we're transitioning this model to NOAA's Space Weather Prediction Center, which is the US's official provider of real-time space weather alerts and warnings. And so we hopefully that's being transitioned in the next few months to a year. And just an example of one of the some of the operational outputs. We want to show things like the O/N2 ratio at the bottom left there, and just watch the neutral density response. This is just an animation from the model of the neutral density anomaly at the bottom right there, and you can see that it actually saturates at the. It'll start up again, and you'll see the gradual build up. The gradient, since the scale there was 100%, maximized 100%, in this particular storm, which was the March one, it exceeded the 100% after about 2/3 of the way into the storm. But you can see the enhancements and the wave propagation and the gradual build up of neutral density. That's actually in the recovery just there, but I think it'll go, if we go through again, you can watch the development of that, and so you can see that development of the neutral density. This is the changes in the neutral density in percent. And on the left is the changes in the O/N2 ratio, then where the positive and negative phases of the atmospheric storm might be as a consequence of that. And you can see this squeezing of this region of increased oxygen. So this would be the region of decreased N2, and this would be the region of increased N2. The more N2 there is, the faster the recombination, the more likely you have a negative phase atmospheric storm. And of course, you can do the same thing for the total electron content. And on the left there, you can see the total electron content on the top left, and then the anomaly, the change in percent terms. You can see the build-up at mid-latitudes. You can see these SED features. And over on the right is just another operational product. What is the possible maximum usable frequency for HF propagation? And just to highlight that, just an indication of those plasma buildups during a storm on the top left there. This happens to be the March 2013 storm. And you can see the buildup of plasma. These are the plasma increases and the SED feature. And it's those features that cause these, on the edge of these features, you get steep gradients, which can cause the impacts on radio wave propagation, and particularly things like the outages of over the US, at least, the civil aviation wide area augmentation system. So just briefly on the horizon, as I said, the weather model now uses the non-hydrostatic finite volume cube sphere FE3 model at high resolution. And that actually contains a lot richer wave spectrum, and we'll hopefully be able to use that in the near future. And of course, we can just increase the resolution in the first place to about 50 kilometers. So we capture most of the wavelengths of the features that you get apart from the atmospheric irregularities. So we're trying to do that. And also trying to extend the data assimilation to higher altitudes, to start with 100 kilometers and then eventually, of course, the whole atmosphere. Because the better we can control the wave propagation into the thermosphere, atmosphere, the more likely we are to predict the triggering of atmospheric irregularities. So briefly, to summarize, the WAM-IP at the 200-kilometer horizontal will be transitioned to operations at NOAA sometime during this current fiscal year, hopefully. It's an extension of the weather model. The weather model uses data assimilation below 60 kilometers altitude, so we're able to follow the real weather events and their impacts on the upper atmosphere. And of course, it also responds to changes in the solar and geomagnetic activity, especially during a storm, which of course then tend to dominate. And we have shown that actually just the wind and wave fields, even from the lower resolution version, can drive day-to-day variability of atmospheric irregularities. And so hopefully by increasing the resolution, we'll be able to capture the full spectral waves and improve that propagation of waves and forecasting the atmospheric irregularities. And of course, we'll benefit from all the improvements at EMC. Thank you very much for your attention.